So we're talking about light and matter, lightning bolt, because that's light. And we have wave model, particle model, and matter down here. And the key to doing this is to remember there's an experiment. Young's experiment is the wave experiment, and it has formulas and there's a bit of theory, and it tells us a few formulas on the side, like some wave formulas about light. Then we have the particle model, which is the particle experiment, and this tells us some formulas against some theory, and these will be the main questions you get. But then it's good to have these formulas, but I'll go through them in a second, and matter down the bottom. Okay, so I'll start with Young's experiment. Young's experiment, light comes in through two slits, and you get a whole bunch of maximum and minimums. The theory is that if there's multiple bright spots and dark spots, it means there must be some kind of interference. Like, this makes sense if light was a wave. Like, you can imagine waves making bigger and brighter and softer spots because of cancellation. But if it was just particles, you just end up with two bright spots. So that's the theory behind it, interference, which is a wave phenomenon. And this is also our diagram. So this D is our slit difference. This lambda is our wavelength. This length is the length between the two places, and width is the width between the bright spots. And there's only two formulas for Young's experiment, actually. Path difference, which is n lambda for bright spots, and then plus half lambda for dark spots, and fringe spacing relationship, which is a way of relating the width between the bright spots to all these other variables. And we'll go through an example of how to use both these formulas now. So we'll start with the second formula, actually, fringe space relationship. Which of the following will increase the distance delta x between the dark bands in the double slit? So the fringe spacing, I can put my formula somewhere. I'm sure I can put it. So I'll just write it here. So I know I need to use this fringe space relationship because increasing the distance between dark bands, this is the fringe spacing. Yeah. So if we increase the fringe spacing, all of these things will increase. So we need this formula, because if you notice, the path difference formula has nothing to do with the distance between bright spots and dark spots. Okay. So which of the following will increase the distance between dark bands in this? So we have our formula, and what we want to do is increase W. So let's just put W on the side, and equals L lambda on D. And now we can just go through and think about it. If we decrease the slit width, so that's the width of the slits. This formula doesn't have anything to do with them. D is the separation between the slits. Just like we showed you. See, it's the separation. The slit width would actually be how wide they are, and that doesn't affect this. Decrease the slit separation. If we decrease D, since it's on the bottom, this W is going to increase. So that looks like a good answer. But we'll keep going. Decrease the slit screen distance. If we decrease L, which is the slit screen distance, I'll bring it back over here. Slit screen distance. If we decrease that, L, then obviously, if we decrease L, W will go down as well. So decrease L leads to decrease W. And if we decrease the wavelength of light. Similarly, if we have W and L, if we decrease lambda, we decrease W, because they're both on the top. And decreasing something on the top equals decrease over here. Whereas if you decrease something that's divided by, like W is proportional to 1 over D, as this gets smaller, W gets bigger. So that's why it's opposite. So our answer would be B. Now, to use the path difference formula, there's only one situation, or essentially one kind of situation where you want to get. They're like, what is the difference in length, which is the path difference? So when you see these S2, P2, S1, P2, what does that actually mean? S2, P2 is the distance here, from S2 to P2. Subtract S1, P2 is that distance, and the difference is the path difference, which, as I showed you back on this diagram, would be lambda for would be lambda between for like if it's between consecutive like bright spaces. Yeah. So when I put this width in here, this is between two consecutive bright spots. So here, what is the path difference where P2 is the second maximum away from the central axis? we know it's a maximum, so we know we have to use n lambda. If it's the middle one, we use 0 for lambda, so that's the middle. If it's the second one, we use 1 for lambda. If it's the third one, if it's the first one, if it's the second one, second bright spot, then we use 2 lambda. So what does this mean? The path difference, this path difference, at our second maximum, this path difference will have to equal 2 times the wavelength. So we just need to find the wavelength to figure out this path difference. Luckily, we have it here. Path difference equals 2.8. Wavelength equals 2.8. So therefore, the path difference is 2 times 2.8. Essentially, that's most of the formulas you need from light, from Young's experiment. Whenever you see Young's experiment, you need these. Let's all try it out. I'll give up some examples soon. In terms of theory, explain what Young's observation of bright and dark regions tells us about the nature of light. Essentially, what we want to say is, instead of 2 bright spots, we had multiple dark and bright spots. And that means we must have had effects like interference. Interference, which is a wave phenomenon, and therefore light must have some wave properties. And that's Young's experiment. Probably go over these formulas in a different video. Yeah, that sounds good. We're going to move on to the photoelectric experiment next.